Okay. Good. All right. Good morning. Welcome, everyone. My name is Raksha. I'm very happy to introduce you to Sashka, who's our presenter today for this tutorial on deep learning. And he can tell you more about it, but he's our friend and partner at Brainly with Eric, who some of you remember, he was actually our student here a few years ago. And we were just talking about it. Exactly 3 years ago, he graduated. So today is a graduation day, and 3 years ago on this day, he was walking. They grow up so fast. And so now Eric and Sashko work at this company called Brainly, which is a question answering service. It's based in Poland, but they're expanding in other countries. They have a big presence in Europe, and they're also expanding in other countries, including here in the United States. They have office in New York. So we've been working with Brainly closely for the last couple of years, and one of the reasons is, one thing we have interest in question answering. The other thing, we have access to this amazing data from them, which is all text data, a lot of content. And so when you have a lot of content, you have a lot of data, you can do all kinds of interesting things with it. But of course, you'll always be limited by the tools and the techniques that you know. So the goal here today is to maybe pick up a couple of new tools and techniques, even things that maybe you already kind of sort of know. And so using not just Brainly, using not just this particular content, but in general textual content as a way to practice some skills, some tools. And so Sashko is going to walk us through that. The plan is to have, so we have 3 kind of segments, and if you did the RSVP, you probably got an email with some outline that we created. Each part will be about 1 hour long, and then we'll take a break, right? And the goal is to walk through sort of like very introductory things to then a little bit more advanced. Sashko and I work together to make sure that we create the material, or Sashko has a material that applies to a broad audience. So that also means that you're going to get a lot of just the introductory idea, and then if you really want to go deeper into that, some pointers. Okay. So one thing Sashko promises, he will also give us enough pointers so that if we are interested in any particular idea, then we know where to go next. Okay. So with that, I'll let Sashko, take over.
Hi everyone. I'm
And we have your consent to get recorded, right?
Yeah, of course.
Okay.
Hereby I express my consent. So I spent most of my time now advising startups and primarily Brainly on different things related to machine learning. I used to work for Google before that, primarily on personalized recommendations and text processing. And I'm still conducting some introductory machine learning courses for them. Unfortunately, it turned out that I cannot reuse those materials because it is not public yet. So I came up with copy-paste of illustrations from internet mostly. But let's see how it goes. Otherwise, the content is the same as in the plan, which Chirag shared with all of you, I think. I took some shortcuts because it originated as an idea to make a tutorial, but really as I added more and more stuff for beginners, this became more of an overview than a tutorial, which means you cannot take this material and implement the system end-to-end now. But where possible, I tried to include links to the stuff that will really teach you end-to-end. Also, sometimes before such events, I have crazy ideas to rewrite everything, and the last crazy idea was today at 2:30 a.m. So if some of the slides are missing, I will be writing it on the whiteboard. And something is inevitably missing. All right, with that, let's start. There will be 3 parts. The first part is like a general and rather shallow introduction to machine learning. Probably Probably most of you are familiar with all these concepts, but just to refresh. The second part is on word embeddings and deep learning, and primarily motivation behind the deep learning. And the third part is about some of the techniques used for natural language processing. So I tried not to include too many formulas there, because 2 weeks ago I conducted a class on information theory, and lots of people were scared. So if there will be formulas, I will write them beside this. These are not important, like this you could look up in Wikipedia or wherever. So with that, let's start. By the way, if you are blocked or if you have some really important question, let's start with this framing that feel free to interrupt me, and then if we lack time, then we'll change this. Okay?
I can give you time, so when we get to the top of the hour.
Cool. Yeah, so this is our working definition of learning for today. I came up with it when flying to New York from Poland, so please don't take it too critically. But it's for today, for the next 3 hours, learning is defined as using observations from the past to optimize our behavior in the future. And machine learning only, modifies the part that machine is doing, not the human being. There is one more thing that everyone knows about, is Zipf's law. Someone calls it power law, but it's more or less, it states that if you make a dictionary and you order words from the most frequent to the least frequent, the most frequent will dominate. So we can say that the frequency of a word in a large corpus is approximately proportional to the inverse rank of the word, right? Which will introduce some of the problems which we'll try to kind of solve or work around today. But this concept of long tail is very important, because in a corpus that is arbitrarily large, there will be inevitably words missing. Like if you are Google and you are accumulating all the news in the world, you would expect like everything to be represented there. It is not true. And also with calculations and with some of the algorithms, we have a problem with the head. The words from the head dominate everything, and sometimes we make a decision to subsample them, to cut this head. All right. So with that, let's start like from the fruit fly of machine learning and lots of other things. It is linear regression. We have some input, which is in our case is high school GPA. It could be like the square footage of a house, and we have something to predict. In this case, it's university GPA. Could be the price of the house. And here, like linear regression makes sense. In lots of the settings, it stops at some point, but we have some good value to make predictions, and we are making predictions. So let's introduce some terminology based on this. So we have a feature. A feature is something that we are given as an input, right? In this case, it is high school GPA. We have a label. In this case, it was university GPA. So it's something that we need to predict, but also in the supervised learning setup, it's something that we are given, at least for some of the examples. And the next notion is the example. It is like a piece of the information. It's a data point. And in supervised learning, they come in two flavors, labeled and unlabeled. Labeled is something we can learn on or test on, and unlabeled is something we need to do inference for. So in general, both in the academic literature and to a large extent in production, there are two distinct phases of using the system. First, we are training the model, then we are using it to predict stuff. There are, of course, fancy systems which learn online, but this is much less spread than most of the people pretend. Yeah, if there are any questions or you disagree with something, feel free to comment. And then for linear regression, how do we fit a line? We introduce the notion of loss function. Loss function is how bad our model is at doing what it is supposed to do. And in the case of linear regression, we may measure the distances between the actual points or the labels and our predictions. And in lots of cases, they start with L2 laws because it mathematically it originates from something beautiful, from statistics, and also the major thing is that it's easy to take the derivative. So we adjust this line in order to minimize the loss. And let's introduce TensorFlow really briefly because I'll be using it in a few examples. Again, this is not a tutorial, so I'll be like using copy-paste of the code to illustrate that it's not hard to do things, not exactly to tell how to do things. So TensorFlow is open source, it's not machine learning specific, it's just an API in a way to build computation graphs and run them. But there are high-level APIs built on the top of TensorFlow, which are machine learning and deep learning specific. So for now, I guess it still holds true. For now, they only have Python API for training, but they have APIs in different languages for inference. Some of them, especially this high-level stuff, are not stable. When I first started conducting these courses in Google, there was this TF-Learn. And in TF-Learn, there was just enough to cover the functionality which was included in the tutorial. So one step to the left, one step to the right, and you should try to roll. Yeah, and some of the features, especially if you want to run on GPUs or you want to run fast or distributed, they require building TensorFlow from sources. A quick note to those, if there are some of you in the audience who come from physics or like some mathematics, here we define tensor as multi-dimensional array. There is nothing like specific magical transformation in spaces, at least here. And it doesn't necessarily have to be an array of numbers. Different other types are supported there. But again, mostly numbers, since these are calculations. So this is one of the few slides with the code. How to define a linear function. So there is a notion of session. Session is kind of something that connects client and server. They have this client server. If you're familiar with OpenGL or stuff like that, then you know that the client builds the stuff and the server executes it. So we define a variable. Here it's just a scalar. It can be a tensor of arbitrary dimensionality. So weights and bias or intercept. And then we define a placeholder. A placeholder is kind of a value which will be told later to the graph. And we calculate this result. So this is the standard form for linear function, but you know these coefficients they come in many different letters. Here it is W because of weights and B because of bias, but it can be anything.
So Sasha, so what is the purpose of, I mean, other than, is it just learning the regression line?
So it was not even learning, it was just defining the portion of the graph that calculated that tried to predict y based on x with a given weight so far.
But I mean, you could do this with anything pretty much, you know, I mean, I'm trying to understand why would you use TensorFlow library. So.
Okay. So among other things is because if you are with TensorFlow, then you could do both low-level stuff like this, and with like TF-Learn APIs, high-level stuff like you can define the convolutional layer just with one line of code or maybe a few lines. You could like define a portion of the graph that would be a sequence-to-sequence recurrent neural network model with a few lines of code. So for me, the positive thing is that you can combine low-level and high-level stuff and mix it. In most of the libraries for deep learning, I don't have this luxury. I can define layers and work with them, or like with some mathematical libraries, I can only do low-level stuff and it does not mix well. Here it mixes well primarily because it all operates with these concepts of graph nodes, and graph nodes are tensors after all, like placeholders for tensors. So that is the positive thing for me. Also, like, it's supposed to be cross-platform. Nothing cross-platform is really cross-platform in every setting, right? So there are things that run only on CPU, there are things that run only on GPU, but still overall it runs pretty smoothly compared to like earlier efforts to build libraries for machine learning. And for me the good thing is that it's open source, but it's backed by Google. So Google had this plan to make TensorFlow lingua franca of machine learning, first within it, and I doubted that they would succeed, frankly speaking, because there were so many machine learning related projects, and everyone seemed to like writing their own code for calculating stuff. But it looks like they succeeded, so I think it will not die within the next few years. So that's a positive thing for me. All right, and here we define the L2 loss. So y underscore is like the correct value, and we take the square of the difference, and then this reduce sum. So reduce in the terms of like map reduce, not that we try to lower it. So here we just define the graph to do the inference in a way and calculate the loss. So now how do we minimize the loss? We minimize the loss, at least for now, with the pretty naive approach of vanilla gradient descent, meaning that we take the derivative of the error, and then we try making small steps into the direction of negative gradient. So this is like a nice example of convex problem, right? We could actually find the global minimum even in closed form without any gradient descent. So this is just an illustration. And here is how we do it with TensorFlow. So we define optimizer. This is the thing that calculates derivatives and takes these steps for us. And this parameter is really important, especially in the gradient descent in its simplest form. This is learning rate. This defines how large will be the step that we will take. And here we try to minimize loss, but this is just the definition, right? We are not running anything yet, we're just building the graph. So why this learning rate is very important? If the learning rate is small, then your convergence will be small. But that's just a problem of time in a way. Well, if you have just, a limited time with some resource, it's not a small problem of time, but still. But the problems arise if the learning rate turns out to be larger than needed. So you may start pretty close to the minimum, but then if your learning rate is too high, you will jump on the other side and you will end up actually further away from the minimum. And then if you continue this way without any decay on the learning rate, you will go up and up and up, and you will go to nonce, and your learning will like terminate at normal. This is all pretty easy if we have a simple loss function like here. It becomes harder with the complicated losses because we cannot reasonably expect what the gradient will be at some of the portions of the range. So there are adaptive methods of finding the minimum, and I think we will not cover it during this talk. If you are interested in chatting about it, then let's do it in the break. But I think for you to remember, there is this gradient descent optimizer. It is not the only optimizer which you can use. The other widespread things are ADAGRAD. This is like shortened from adaptive gradient descent, and also ADAM optimizers which do things that are pretty close. They often apply decay to learning rate, meaning the further we go in the training, the lower learning rate becomes, but with these adaptive methods, at least with most of it, it is done implicitly. Okay. And here we actually train stuff. We set some training data and we initialize variables. This is not too important to remember because I will give you links afterwards. And here we make 1,000 iterations of taking this step. So a few more words about gradient descent. You could often see the notion of batch size. So what is batch size? Historically, when they approached optimization problems, they tried to optimize on all the data set, and this is called batch gradient descent. When you're optimizing using only one of the examples, this is called stochastic gradient descent, that sooner or later it will come pretty close to the minimum. So mini batch is kind of an optimization technique, performance optimization. Especially if you are running on GPU, it makes sense to take like as much data as you can and make computation. But with this mini batch size, you should be careful because if the mini batch size is too large, then the model will be prone to overfitting. It will find some local minimum and it will never go out of it. The intuition behind it, so as far as I know, there is no real proof. But the intuition is that with small batch sizes, it acts like a randomization mechanism. You could see it as like adding some noise to your inputs, which in general is one of the regularization techniques, and it allows system to generalize better. But this is like stuff to experiment with. All right, and here we evaluate our model. Again, it's just for illustration purposes. You don't really have to even do it with high-level APIs. But we tell this session to run with the given x's and y's, and we calculate loss among other things. And here's the output of weights and loss calculation. Okay, and here are the links I promised. So on TensorFlow.org, the copy-paste of code from documentation did not always work, but from version 1.0 it improved a little bit, so now you can reasonably hope that if you take stuff from the tutorial, it will run. So get started is the really basics, and tutorials are more specialized. There's also the thing called Deep Playground, and sorry for this color, I think it will be more readable at your computers. I think we'll share the slides. Right? Sure. So Deep Playground allows you to build intuitions on how neural networks, among other things, run and learn. But also, if you delete all these hidden layers, what you'll get at the end will be linear regression or logistic regression, depending upon the problem type. So it can be classification, it can be regression. And then you can play with different learning rates and problem sets. So the colors are very unfortunate. So there are sets that are linearly dividable. There are some that are not, like here, and then it's fun experimenting with it. Of course, the data comes only in 2 dimensions, so it does not tell you much about how it acts in high-dimensional spaces. But still, this allows you to develop a reasonable intuition. All right, so now for generalization and overfitting. If we learn from the past and if we want to use it for the future, we want to be able to make inference for the examples that we've never seen before. They will be hopefully similar to what we've seen, but not always. And after all, if we just need to make inference for the examples that we've seen, we can end up with, lookup table and be done. So in general, they have this it's called prior belief, one of the prior beliefs in machine learning that is widespread, that it is smoothness prior. It is that there exists some space where things that are close together are similar. And lots of techniques for regularization act on this prior. And even most of the models that are used in the real life, like neural networks in general, they are like assuming that at some level the data is smooth. In order to test if your model is overfit, you generally divide your data into training and test set, or into training and validation and test set, not to overfit for the test too much. And then it's extremely useful to plot your loss, to plot some metric of model performance in time as it trains, or as we add more parameters. And usually it looks like this. So there will be one line for the training set and another line for the test set. And in lots of cases, this line for the test set, after some time, it actually goes up. So what we do is stop training. It's called early stopping, unsurprisingly. When we have worse results, when we start getting worse results for the holdout set, we will stop the training. Another approach that could be used is, again, some sort of decay for the learning rate. So it depends upon whether you can afford it or not. Yes?
Is this technique valid for other classification techniques also?
Yeah, everything that can overfit. So if you go and try to be more specific, there is a trade-off between specificity and ability to generalize. So yeah, of course it's useful for everything that can overfit. But also, this is how to tell whether we are overfitting, how to deal with overfitting. And the family of approaches is called regularization, but it comes in lots of flavors. The one we can apply for most of them is L2 regularization, or in general LR regularization. Then this shape depends on it, right? If it's one, if it is square, etc. So what it does, we act on the prior belief that it's good to keep coefficients close to zero and like normally distributed. And so if we add this to our loss, so lambda is one more parameter that you should choose, then the model will try to find the balance between perfectly predicting stuff for the training set and keeping coefficients small. So there is a also L1 regularization, which is widespread in wide models. If you have lots of inputs and you think that some of them are useful, some of them are not, and you like to find those that are useful, you apply this L1 regularization, and it brings those that are not useful to zeros, but you should also be careful with it, because if there are inputs that correlate to each other, that they are dependent, it will kill some of them.
Sasha, can you just say a little bit about regularization? What is it and where do we use it?
So many people link it to Occam's razor. We punish the model for being complex. We prefer like models that describe the reality with the least complexity, and with L2 the sum of the squares of the weights is our metric for complexity. Like with dropout, which we'll maybe see if I did not forget the slide afterwards for neural networks, we say that the model should not over-rely on some of the neurons. So adding noise to the input can be treated as a form of regularization, but then you should be careful. In graphics, it's really widespread. When you tilt the image or you blur the image, and it still should recognize the same. With text, it's You can add misspellings, but then it depends upon your model what it will do. You can try replacing words with synonyms, but again, this can alter the meaning, right? We have lots of synonyms with different connotations. They're used in different contexts, and it usually does not act too well. One of the areas, like related to language processing, where we can use this noise, and it's used everywhere, is speech recognition, because we have all the kinds of background noises, and if we have a library, then it's okay, like, to add noise to our sentence. So it comes in all of the flavors. The thing that unites it all is that it makes model less complex, and therefore it makes the model less expressive. And again, we are acting on some prior beliefs. We are saying to ourselves, oh, this way of being expressive is probably useful, and this is not as useful as the others. And so in general, with priors, like 2 days ago when I conducted this beginner class at Google, there was a lady who approached me, and she's working with some financial data, and she was asking, all this deep learning, it is so cool, we can probably take all of our data and just feed it to some algorithm, and then it will find all these kinds of relations, etc. Because now we are trying to guess. And in reality, when you are designing the model, you are already trying to guess something, right? There is no free lunch. So yeah, wherever you use it, you should probably first of all think to yourself how intuitively it works in your space. And then of course try different kinds of regularization, and always look both at your error at test and training set and see how it is related. There is a pretty common, I would not call it misconception, but it's like a huge simplification that overfitting is because of noise. It's not always because of noise, it's, well, because of how the model interacts with the data, right? It can find some predictor which is really strong, and then act on it, and then think it is good, but it will not generalize. Especially if you're working in the real world with like recommender systems. We train our model for like data on all the year, and now the Christmas season comes and all the patterns of behavior change. Or if we train on data from news, then the new news appear, and then the words are related differently. So when you are using it in production, as opposed to academia, you should not always push for the highest possible results, even on the test set, because so the distributions that we are dealing with in the real life are very rarely stationary. So yeah, let's go. I think we will run over time. Cool. So if we have these simple models already, how to fit text to them? And one of the widespread approaches is the back of words. We just build a vocabulary and assign indices to every word, and then we count the words. This can be just 0 or 1. It works especially well for the short text. This could be count of words. It's a bit too naive. This could be TF-IDF. Everyone knows what TF-IDF is, right?
I think we had one, yeah, we had a few done.
Okay, so it's term frequency, inverse document frequency. Term frequency is just the count of words in a given document. I will not write, probably it's easy to explain. But it can be adjusted for the length of the document as well. Because otherwise you'll get longer vectors for longer documents, which is not always good. And then there is inverse document frequency, and this is the total number of documents divided by the number of documents where you encounter a given word and then take the logarithm of it. So it is kind of how strong a word is. So oftentimes when they build in a vocabulary, they are excluding the stop words, right? So the stop words are things that we assume are meaningless. And this can be done either by cutting this top of the vocabulary, or perhaps a more reasonable approach is to use some vocabulary of the stop words. And then there is inevitably some limit on the size of vocabulary. And then we cut the rest of it, and in many cases replace it with a special tag like a known word or something. And then, so when dealing with these language problems, most of the people choose English, not only because there is lots of data available for English, but also because it is a pretty simple language morphologically. Right? When we switch to like Slavic languages, to Polish or Russian or Ukrainian, this is harder because there are more variants. But we can deal with it by like something that can cut the words, and the system which knows about morphology, right? And then there are languages like German or Turkish where there are all these composite words. But still we can deal with that somehow. But then by cutting the words, we also act on some prior beliefs. We say that, oh, this is probably a noun, and then I should cut out this and this. This is a verb. But then in order to determine the part of speech correctly, you need to understand the meaning, and in order to understand the meaning, you need to have a model, ideally, and in order to have a model, you need to cut the words. So we either, it's a kind of bootstrapping, right? We either act on some stupid, well, simple assumptions, or we go from word level to character level, and it's incredible. The first time I saw a model, a neural network, which does, it actually did the part of the speech tagging, but it took the chunks of character. It was not even characters, these were bytes from Unicode representation into account, and then it typed the word, oh, this is a noun, this is something else. It was like magic to me, because in language I always, so for me this analogy between language and like items in user profile, it is very strong. The one is sequence, the other is sequence, and everything, every element has a meaning, and then you go to the characters and every element stops having a meaning of its own. But then you can act on the analogy with image processing. So a given pixel does not really have a meaning. It can be some predictor, especially if you're working with simple data sets like MNIST, you know, these characters only in one color channel, centered and resized and whatever, then yes, you can build some logistic regression model that does a pretty good job of predicting, and you can actually build these heat maps like which pixels are responsible for what. But otherwise it's only interactions, and maybe we'll have time to talk a bit more about character level later on. So yeah, we take this bag of words, this is our axis, this is the vector, and we choose coefficients for it, and we can do regression with stochastic gradient descent. But what if we need to classify? So there is a pretty simple basic answer. We take a regression model. So all of this is called logistic regression, just in case you, the items are too like simplistic. So we take a regression model and we say, oh, this is a regression model that predicts the log odds. Should I write what is log odds? So you know in betting like 1 to 10 or something, right? So this is odds, and I should not even write it down. And the logarithm of it is called log odds. And it is good for doing calculations if you have to combine probabilities, then you are adding instead of multiplying. And in general, if you have a big system that deals with probabilities, then this is a preferred form of representing probability. And then we transform log odds to probability, and then we calculate loss based on this probability. So, and I think here will be a few formulas. Oh, not really. There is only a graph. So, logistic sigmoid is a function that is used to go from this log odds space to the space of probabilities, and it's 1 over 1 plus e to minus x, if I remember correctly. And it is one of the functions that does the so-called squashing, right? from the infinite, we go to something that is limited between 0 or 1. And yeah, and then we calculate loss. And this is called log loss, or you may know it by the name cross entropy loss. So it is pretty simple. We have an example. We classify it, let's say it's binary classification. We classify it either as class A or class B. So y will be 1 in case of class A, and it will be 0 in case of class B. So this is our target, like this is our label. So in reality, you will have either one part of the loss or another part. And this minus log of P is our predicted probability. It's kind of, you may call it surprisal, among other names it comes in. It is kind of the number of bits that you need to tell about some event, assuming that the probability of the event is P, or like 1 minus. And here in log loss we act on the knowledge that the events are mutually exclusive, and therefore this P and 1 minus. If we have more classes, then we will act accordingly. I think I had a slide on it. Then what if there are more than 2 classes? We can either do one versus rest classification, meaning we train a separate classifier for each of the classes. And this is especially useful if we don't assume that the classes are mutually exclusive. If we are classifying messages from our users, and we say, oh, this can be a customer complaint, or this can be like some positive review, and this can be either about, I don't know, if we are airline, about food quality, about, check-in, about whatnot. So there are lots of classes, and there is a pretty complex structure of, some of them are mutually exclusive, some are not. So the simplest approach would be just for each of them to train a separate class. And here is how the graph of log loss looks. This is for one value, and this is for another value. And you see that there are these nasty functions that try to go to infinity somewhere. And usually for this function, it's good to regularize. But also, if you see this stuff implemented somewhere, they almost always add plus some epsilon to it, for it not to be crazy. Because if we are expecting something to never happen, and then it happens, then our surprise always is.
I didn't understand why we were using this function.
Also, we are using the sigmoid function because we want to go from the log odds to the probabilities space, and this is the stuff that allows us to go through that. So log odds is kind of log of P divided minus PA. Well, we assume that probability is between 0 to 1, right? And then the inverse of it kind of will be this stuff. And also, even if we did not have to, it would still be good for us to go to some range that is closed, so that we don't have uncalibrated things, kind of.
What is the input for this? Like, what is the x in this?
So x in the sigmoid is our result of like ax plus b, some linear function. Where this could be vectors or tenders or whatever. So this is it. I should have called it y, of course, and called this y something else.
So I think the point here is it allows you to confine it to a limited space. So the x could be anything, but then when you apply this function, you get something that's between that 0 and 1. And maybe actually from the graph it wasn't so clear, but if you look at where x goes, it could go anywhere.
Yeah,
But the y is always between 0 and 1.
So for some time, actually this squashing functions were really popular in kind of deep models. They were not called deep back then because they allow to renormalize, kind of. So now they use other activation functions, and then sometimes they do this batch normalization when they say all that. But let's talk about it later.
So, I mean, so just to be firm, like you can try putting different values in that function, sigma 1 over 1 plus e to the whatever, right? So you can put like infinity in that, and you'll see that you'll still get either 0 or 1. You know? So in whatever case, it's covered, right? And so that's sort of the nice thing about it.
But like how reflective is it of like the input? Because we are transforming it, so wouldn't it affect the ultimate probability?
So really, this output of it, these are probabilities. The input is log odds. Yeah, the good question could be like in many companies that I've seen, there is a classifier. Like let's say there is a model for detecting bad messages for brainly. And then they say that the one with like badness score of 10 is a worse message than the one with badness score of like 5 or something, whatever the range is. But then it's not a correct framing, because if we are training the model on like binary labels, 0 or 1, this is the probability that the model is giving. This does not necessarily mean that one is worse than the other. It's like from the point of view of the model, there is higher probability that one will be worse than the other. And people often forget about it, especially if we are recommending stuff, right? Of course, it makes sense to go from the most probable to the least probable, but these are just probabilities. And there is no direct link between recommending things and predicting the star rating, for example. And therefore, if you have like Netflix recommendations, sometimes they would recommend you items with predicted like 3-star rating for you. And it's not that because they would like to recommend you bad content, but that's because they are sure that you will reasonably like the item, something like this. Okay, so if we have lots of classes and all of them are mutually exclusive, we use softmax, and this is like e to the x, if we're still using x, divided by the sum of all these things. And it's only for normalization. And if you think it's hard to write it down, then in TensorFlow it's just like this. And this is both the softmax and so here you actually define this last layer of whatever you have for classification. It's not that hard. So labels are like the true labels, these are zeros or ones, and logits are whatever your regression model tells you are the log odds of things. So even if mathematically it's like one step, then the next step, then one more, oftentimes it's just one line of code. Okay, so from the laws, how do we go to some measurement of the actual performance of a classifier? Because loss, it's like it's average between everything, and then you never know how to operate with it unless you're really familiar with the model. And oftentimes they use accuracy. Accuracy is the number of correct predictions divided by the total number of predictions. And if we have benchmark sets with balanced classes, this is the thing to go with. But in case of class imbalance, it is rather misleading. If we classify people into, I don't know, alcoholics and non-alcoholics, right, and there is 1% of alcoholics, and we say that no one is, then we are 99% accurate, but this does not bring any value. Okay, there was one of the slides missing. And what do we use instead of accuracy? In case of binary classification, we can operate with precision and recall. Should I write it down? Okay. So if we divide all the possible combinations of the like classification as in real world, so this is positive, this is negative, and this is predicted positive, this is predicted negative. There are 4 possible combinations. If it is really possible and the prediction is positive, then we say that it's true positive. If it both are negative, then it's true negative, of course. If it's negative, what we predicted positive, we say false positive, and here we say false negative. Okay? So with this, we define, and sorry if I'm wrong here, I sometimes mix it up. Okay, so precision is the number of true positives in the positives that we find. So in true positives plus false positives. Okay, if we detect like 100 spam messages and we want to remove them, then precision will tell us how many real spam messages we will remove. Okay, and recall is the number of true positives divided by the number of positives in the real life. So these are true positives plus false negatives, I think. And this will say that if in the real world there are 100 spam messages, then how many of them will we remove with our system? Okay, and it can go to the multi-class classification, because for each of the classes we can actually come up with it. Another way to illustrate the performance of the model is confusion matrix. Confusion matrix is the larger matrix between the true classes and predicted classes. And ideally everything will lie on the diagonal of the matrix, but it never does unless we mistakenly, test it on the training set. Okay, there is one more metric which is really widespread. This is area under curve. Receiver operating characteristic area under curve. And this is true positive rate, and this is false positive rate. Yeah, and there is some line here. So we really want to have all true positives and no false positives, which means that we want to cover this point. We never achieve it. And a good explanation, so they say that area under curve equals this and that. What it means, like intuitively, is that if we have one random positive example and one random negative example, like positive and negative in the real world, then what is the probability that our model will rank positive example above the negative example, right? And that's it. And this intuition is useful when we go to negative sampling, because that's what we try to kind of optimize for in negative sampling. We take a positive, we want it to be rated higher than negative, maybe with some margin between them. Okay, so yeah.
So which one you use more frequently in real life from these measures of terms?
From the metrics?
Exactly. So I mean, do you use the AUC, do you use the precision, recall, or accuracy?
So I usually use the precision and recall at least to illustrate it to people, but then I should always say that there is a balance between them, right? So like for this spam detection and removal, I was asking Brainly what precision can we afford, how many good messages can we afford to remove, and based on that I can tell them they recall by just adjusting the threshold. So at least for me this is the easiest to kind of comprehend. The area under curve, I kind of understand what it is, but still if you tell someone, some business guy who doesn't know about statistics, and this kind of people exist, unfortunately, Well, we have area under curve 0.7. Okay. So with precision and recall, it's really important that if you have class imbalance, then you do it for underrepresented class. Because if we have spam detection and we estimate the percentage of spam messages to be like 5, okay, and you go to some contractor and they say, and actually I came across this in the real life, and they say, okay, we will detect good messages for you, and we'll have like good precision and good recall, but it's like trivial. You say that everything is good and then you have everything covered, right? So even in case of class imbalance, of course, there are always things that logistic regression works imperfectly in class imbalance and people start some sampling. I much more often see the problems with how people measure. Because they have class imbalance, they use accuracy and then they are saying, oh, we are fine. But this is a classical example. Okay, so with model complexity and data availability, first of all, if you say that we have like, let's say you make a universal image classifier, right? And then you say we can detect, like we can define the category of every image. One of the categories is car, and then you should ask yourself a question, how many images of, I don't know, Tesla Roadster taken from underneath do I have? And it will turn out that it's like uncomfortably close to 0. So when you're judging about the size of your data set, you should always ask yourself what are the underrepresented categories and how many examples of them I have. Of course, it's possible to generalize, but still this is something to start with, not the general number of data points. And then, yeah, start with a simple model and increase its complexity and try plotting training versus test loss and see how it interacts. And then, at least with text, it's easy to retrain things on open data or some unlabeled larger set of data. But then you should again care about the similarity between this set of data and what you really have. Like with word embeddings, which we will discuss a bit later, people use this pre-baked embedding straight mostly on news or Wikipedia, and then they have some system with special vocabulary, and they are wondering why it does not really work. Yeah. Yes.
I guess really quickly, one thing I wanted to ask about the precision and recall. So this is to complement our, say, like we get like a high accuracy score. Say, like taking this example of like 99% non-alcoholics and 1% alcoholics. So we have like a high accuracy score, but we also want to do precision and recall. We want to do that relative to relative to the label, so whether it's 1 or 0. So if we have like force, I guess we have force scores then, and then we look at those. Is that right? Or
no, we take the smallest class. Like if we have 2 classes,
yeah,
we take the smaller one.
Okay, so we take the smaller one as a positive class.
Yes.
And then we do precision and
yes.
recall.
Because we can do it for everything, right? But it does not make too much sense to do it for the dominating class, just because the values will be high. Of course, if you want to like impress someone because then this is the way to work. Yeah. So like this is the conclusion of this first part. Here is a standard. V here is not only because of my bad knowledge of English, but also because it is the course that most people are taking. It's the Coursera course by Andrew, and 99% of people who are taking it are happy with it. No, I'm kidding. All right, so I think.
Yeah, so I think this is perfect timing. We're going to take a very short break and then come back. The second part, just to kind of give you an idea, the topics are representational learning, giving some motivation about why deep learning, talking about neural networks, word embeddings, convolutional neural networks for text processing. So these are the topics for the second part. And then we'll have the lunch break.
Yeah, I think the convolutional neural networks will be left for the third here are a few links on information theory. I really encourage you, at least those of you who are not familiar with the concepts of these, to read at least this one, Visual Information Theory. It's really a blog post, not even a book or something. All of the rest are books which are like open, which are downloadable from the internet for free. But information theory will give you a really nice intuition of how classification works, why the cross-entropy loss is called this way, and